Hi everyone, this video is about slope deflection equations, second part. So this addresses the different problems you encounter on slope deflection equations. And I have here so many examples uh, uh, selected in such a way that all the possible situations that you might encounter will be discussed here. So if it is your first time in my YouTube channel, please don't forget to subscribe and so that I will be inspired more to do more videos related to your uh, to the course that you're enrolled in, especially civil engineering. So I hope that you will enjoy watching and you will learn from my lecture videos. So, thank you.
So let's have the discussion of example 3 for the continuous beam and load shown. Compute the nodal displacements and reactions forces. So this is the beam, and let's have our slope deflection equations. But before that, let's have these strips. So let's use or compute relative displacements. Let's make IBC as our I, so that 150 divided by 200 is 0.75 of I. So IAB is 0.75 of IBC, and IBC is simply I. And ICD is 1.25 I. 250 divided by 200 is 1.25. And let's make EI equals 1. So let's consider the strip in computing for the fixed moments of AB. So there's no problem. It's just 18 dx. Our x is from A, measured from A to the centroid of that strip. So therefore, the distance of the centroid of the strip from B is 4 minus x. Likewise, for this triangular load, our x is from the zero load to the centroid of that strip. Let's call that x. And since 30 divided by 3 is 10, so the height of the strip is equal to 10x if you apply similar triangles. So we're now ready to set up fixed moment or moment equation for A to B. So moment AB, A is our near end, is equal to 2 times EI, which is 0.75 over 4 over the span, 2 times theta A0 plus theta B, then minus 3 times delta over L, because A and B are supports that do not settle, so 0. Then the fixed moment at A, which is A is in the left side, is negative, so integral minus integral 0 to 3 of differential force P is 18 times dx, the area of the strip, times distance of that centroid of the strip from A, which is x, times the square of the distance of the centroid of the strip from the right, which is B. So which is 4 minus x squared divided by length squared. So simplifying, moment AB equals 0.375 theta B minus 729 over 32. Likewise, moment BA is equal to 2 times 0.75 over 4 times quantity 0 plus 2 times theta B minus 0 plus integral 18 dx, x squared this time, then 4 minus x over 4 squared, 0 to 3. So simplifying, moment BA equals 0.75 theta B plus 567 over 32. Call that equation 2. Next, we proceed to span BC. Moment BC, B is the near end, is equal to 2 times EI, which is 1 this time, divided by span, which is 5 times quantity 2 theta B plus theta C minus 3 times 0, minus integral of 10x dx times quantity 2 plus x or x plus 2 times 3 minus x squared. where x plus 2 is the distance of the center of strip from B, and 3 minus x is the distance of the strip or center of strip from C, which is, because this is x and the total length is 3, so 3 minus x quantity square. So simplifying, moment BC is 0.8 theta B plus 0.4 theta C minus the value of the integral is 8.64. Then moment CB is 2 times 1 over 5 quantity 2 theta B plus 2 theta C minus 30 plus integral of 10x dx. This time we interchange the squared factor. This time x plus 2 is squared, then 3 minus x over 5 squared. Moment CB is equal to 0.4 theta B plus 0.8 theta C plus 22.86. So later on you will gain experience that for one span, you just interchange the coefficient. So before it was 0.8 theta B plus 0.4 theta C. This time it's 0.4 theta B plus 0.8 theta C. It only matters the value of the fixed end moment. Then finally, moment CD. CD has the far end, D roller supported. So we use the alternate formula for moment equation in slope deflection equations, which was moment CD equals 3EI over L. L is 6 this time and I is 1.25. Quantity theta near, so theta C minus P, and P is delta D over L, which is 0. Then minus fixed end moment near, which is negative. Then minus 1/2 fixed end moment far. The fixed end moment far would be positive. So moment CD is 3 times 1.25 over L, 6, theta C minus 0, minus 40 times 2 times 4 square over 6 square, plus quantity, of course, 50 times 4 times 2 square over 6 square, minus 1/2, 40 times 2 square times 4 over 6 square, plus 50 times 4 square times 2 over 6 square, which is this. So take note that the left hand moment at C is negative. So negative, negative for these two loads here. Then the right end, it's positive. But this formula minus 1/2 fixed end moment far is fixed negative 1/2. And that's the fixed end moment at the far end. You just interchange the squared term from here. So simplifying, moment CD equals 0.625 theta C minus 800 over 9. Call that equation 5. Let's now apply equilibrium equations, which is at B, moment BA plus moment BC equals 0. So this is moment BA and plus moment BC, equate it to 0. Combining like terms, we have 0.75 plus 0.8 is 1.55 theta B plus 0.4 theta C equals negative 7263 over 800. Call that equation A. Next, apply equilibrium condition at C. Moment CB plus moment CD should be 0. In other words, they are equal. Moment CB and moment CD are equal but opposite in signs. That's why the sum of the moments CB and CD must be 0 or in equilibrium. So moment CB is equal to 0.4 of theta B plus 0.8 theta C plus 22.86. Moment CD is 0.625 theta C minus 800 over 9 equals 0. Combining like terms, so 0.4 theta B plus 1.425 theta C equals 29713 over 450. So there are only two unknowns, theta B and theta C. Solving these two equations simultaneously gives theta B equals negative 19.206 over EI and theta C is positive 71.727 over EI. The negative sign means, because this is slope deflection, counterclockwise. But the counterclockwise rotation is actually the positive rotation. The global positive rotation. And theta C 51.727 over EI means the tangent at C rotates clockwise because this is positive. But clockwise rotation is negative with reference to the global and universal approved signs for rotation. Therefore, our answers for theta would be theta B is equal to positive 19.206 divided by EI. Our EI is E 200,000 megapascals times I, which is 200 times 10 to the 6. This is our reference I. So that would be converted to kilonewton meter square. So 200,000 times 200 times 10 to the 6, that would be Newton nm square. We divide 1,000 cube to make it kilonewton meter square, and the result would be 40,000. So dividing theta b by 40,000 will give us a value in radians equal to 0.004815 radian. Again, this theta b is the means that the tangent at B rotates counterclockwise, and counterclockwise is positive. That's why these are the results by slope deflections. But our answers for theta B would be based on the universal rule or global rule. So it is counterclockwise, so it is positive. So 19.206 divided by 40,000, that's the result. 51.727, it should be negative. Divided by 40,000 is negative 0.00129375 radian, or this is clockwise rotation. So having found these values of thetas for the rotations, actual rotations, but we will use these values here in computing for moment AB because these equations were set up based on slope deflection convention. So moment DC, which is equal to 0, D to C, so it is equal to 2 times I, which is 1.25 over L6, times quantity 2 theta D plus theta C, which is already found, 51.727 over EI, actually, but 1.25 is 1.25 of EI, so we do not put EI here, anyway they will cancel out. And minus 3 times 0, then fixed moments of D, because D is right of C, the fixed moment in the slope deflection equation here is positive. So it is equal to 40 times 4 times 2 square over 6 square plus 50 times 2 times 4 square over 6 square. So solving for theta d, so we have to transpose this first to the left, so negative, then multiply by 6 divided by 2.5, then after that minus 51.727, then the answer divided by 2, that would be theta d. So negative 100.530 over EI. This is counterclockwise based on slope deflection equation, because in slope deflection equation clockwise is positive, but this counterclockwise rotation is actually positive. So you divide that by 40,000 and the sign will be positive. So theta d is 0.00251324 radian counterclockwise or positive. Then let's solve for the moment at A. The moment at A is simply moment AB. So 0.375 AB, 0.375 of theta B, which is negative 19.206 minus 729 over 32. So moment A is negative 29.984 kilonewton meter. So the sign is final. Negative means counterclockwise, but remember, positive bending is to have a smiley face. Because this is counterclockwise, clockwise is positive, remember. But in the smiley face or positive moment, the moment at the left should be clockwise because it is counterclockwise. That's why it's negative here. And this is the correct sign of moment also. Moment B is moment BC. So 0.8 of theta B, which is negative 19.206, plus 0.4 of theta C, 51.727, minus 8.64. So getting the value, negative 3.314 kilonewton meter. So this is also the final answer because the meaning of this is counterclockwise. B to C, the positive moment should be clockwise at B, counterclockwise at C, but this is negative, so it is counterclockwise. That's why that's the final moment at B. Then moment at C is moment CD, so this is equal to 0.625 of theta C minus 800 over 9. Moment at C is negative 56.5595 kilonewton meter. So let's proceed to compute for the reactions. So these moments here are the directions would be moment A, counterclockwise, remember, 29.984. So this is now positive because this is counterclockwise. At BA, it's clockwise. So moment BA actually is moment BC, which is the negative of moment BC. So it's positive because it's clockwise here. So that's the direction. But moment BC is again counterclockwise, which is 3.314. Then here clockwise, 56.5595, then 56.5595. So to solve for the reaction at A, all we have to do is consider AB and sum up moments about B. So RA times 4 plus moment at B equals moment at A plus the moment of the load, which is 18 times 3 times 2.5. And we will do that in the next slide. So RA times 4 plus moment at BA, which is 3.314, equals moment at A, which is 29.984, plus the moment of the load, 18 times 3 times 2.5. So RA is 40.4175 kilonewtons. Then summation forces Y equals 0 to solve for shear just to the left of B. So you can do that. Then you can consider BC to solve for shear just to the right of B. Then after computing shear B left and shear just to the right of B, you add them. That's the reaction at B. And I will leave that to you to solve for R sub B. Anyway, the answers are provided here. And I will leave that to you to solve. For R sub D, we can isolate CD, summation moment about C equals 0, to solve for reaction at D. So R sub D times 6 plus moment at C, which is 56.5595, equals 40 times 2 plus 50 times 4. So which is now this equation here. So solving for R sub D is 37.240 kilonewton. Again, for RB and RC, I will leave that to you. First, summation forces Y, considering AB to solve for the shear just to the left of B. Then after that, you consider BC, you sum up moment about C equals 0 to solve for the shear just to the right of B. Then summation forces Y at B equals 0. Then R sub B is simply the shear just to the left plus shear just to the right of B. Similarly, for reaction at C. So after we found RD, which is 37.24, summation forces Y for CD, you can solve shear just to the right of C. It is equal to 40 plus 50 minus 37.24. So you get shear just to the right of C. Then you consider BC, summation forces Y, because you already found shear just to the right of B. You can solve shear just to the left of C. Then shear just to the left of C plus shear just to the right of C is the reaction at C. Okay, let's have example 4 for the fixed end beam. Fixed ended beam shown. EI is constant. Determine the nodal displacements and the support moments and the reactions at C. Just at C. So this is the figure. First, let's have a strip. So for this load AB here, If we denote x as the distance of the centroid of strip from from the 24 kilonewton load as x, and we imagine that we have two loadings, rectangular and triangular. The intensity of the load for the triangular load is 36 minus 24, 12, and 12 divided by 6 is 2. So therefore, the height of the strip is 24 plus 2x. Then for this triangular load here, if the height of the strip is here and we denote this distance as x from the zero loading to that centroid of strip as x, then since 27 divided by 4.5 is 6, the height of the strip is 6x. So we can now set up the slope deflection equations for AB. Moment AB is 2 times EI1 over 8 times 2 times theta A, theta A is 0 because that's fixed, plus theta B minus 3 times delta over L. Delta is 0 because A and B is horizontal, or A and B are supports. There's no relative displacements, or the supports do not settle. Then minus the moment, fixed moment at the left end A is equal to the integral of differential force, which is dP, and dP is height of strip 24 plus 2x times thickness dx, divide then times distance of the strip from A, which is 6 minus x, then distance of strip from B, which is x plus 2 quantity square, all over 8 square. So moment AB is equal to 0.25 theta B minus 151.65. Call that equation 1. Moment BA, on the other hand, is equal to 2 times 1 over 8 times 0 plus 2 times theta B minus 3 times 0. This time plus integral 0 to 6, 24 plus 2x dx times 6 minus x squared times x plus 2 quantity square. X plus 2, it's 6 minus x, that is squared this time, all over 8 square. So MBA is equal to 0.5 of theta B plus the value of the integral, phase and moment, 109.35. Then we proceed to BC. Moment BC is equal to 2 times 1 over 8, this one is 8, times quantity 2 theta B plus theta C minus 3 times 0, minus integral of 6x dx times quantity 2 plus x, then 6 minus x quantity square. The distance of the strip from C is 6 minus x because that's overall distance is 6 and this is x. So 6 minus x square divided by 8 square. So moment BC is equal to 0.5 of theta B plus 0.25 theta C minus 41.006. Call that equation 3. Then moment CB is 2 times 1 over 8 times quantity theta B plus 2 times theta C minus 3 times 0 plus integral of 6x times dx times x plus 2 square times 6 minus x over 8 square. So simplifying, that would be 0.25 theta B plus 0.5 theta C, then plus 64.357, equation 4. Then moment, we proceed to CD. By the way, the moment at D is, moment DE is negative 30 times 3, so negative 90, but moment DC is positive 90. Because moment D is negative 90, then moment DC is positive 90. So moment CD is equal to 2 times 1 over 5 times quantity 2 theta C plus theta D minus 3 times 0, then minus quantity 30 times 2 times 3 square over 5 square plus 42 times 4 times 1 square over 5 square. Simplifying, moment CD is equal to 0.8 theta C plus 0.4 theta D minus 28.32, equation 5. Then moment DC, as I said, is positive 90, and it is equal to 2 times 1 over 5 quantity theta C plus 2 theta D minus 3 times 0 plus, because this is the right end, so plus 30 times 2 square times 3 over 5 square plus 40 times 1 times 4 square over 5 square. So simplifying, this is our working equation to solve for the nodal displacements theta B, theta C, and theta D. 0.46 theta C plus 0.8 theta D plus 48.72 equals 0.4 theta C plus 0.8 theta D equals 48.72. So let's call that equation A. Then let's apply equilibrium at B. So moment BA plus moment BC should be 0 because moment BC and BA are numerically equal but they have opposite signs, so that's why the result should be 0. Moment BA is 0.5 theta B plus 109.35 plus moment BC 0.5 theta B plus 0.25 theta C minus 41.006 equals 0. So simplifying, that's theta B plus 0.25 of theta C equals negative 68.344. Call that equation B. Then at C, apply equilibrium. Moment CD plus moment CD equals 0. So CD is 0.25 of theta B plus 0.5 theta C plus 64.357 plus quantity 0.8 theta C plus 0.4 theta D minus 28.32 equals 0. Combining like terms, so theta B, 0.25 theta B plus 1.3 theta C plus 0.4 theta D equals negative 36.037. So solving these three equations simultaneously using your calculator, you will have theta B equals negative 59.9076 over EI, theta C equals negative 41.7455 over EI, and theta D equals positive 81.7728 over EI. Remember, we use slope deflection here, and clockwise rotation is positive. But this negative rotation here means counterclockwise, and the actual slope would be positive if they are counterclockwise. So therefore, for the slopes, we get theta B equals positive 57.9076 over EI, meaning of that it's counterclockwise. Theta C is 41.7455 over EI, and theta D is negative 81.7728 over EI. But when we compute for the moments, because we already established these moment equations here, we use the original values as results from slope deflection equation. So for theta B, we substitute negative 57.9076. For theta C, negative 41.7455. For theta D, 81.7728. So for moment A, so moment A is equal to moment AB, 0.25 of negative 57.9076 minus 151.65. The result is negative 166.127. The meaning of negative 166.127 is the moment is counterclockwise. And because we expect clockwise moment to be positive, remember, if the bending is smiley, the moment is positive. And for that positive moment, at the left side of that beam, the moment should be clockwise, and on the other side, it should be counterclockwise to have a smiley face. But because this is counterclockwise, that's the final value, it is really negative moment at A. Moment at B also is also final after we substitute theta B and theta C. So it is moment B, moment BC, 0.5 of negative 57.9076 plus 0.25 of theta C, negative 41.7455 minus 41.006. And it is negative 80.396, and that's the final value. Moment C is moment CD, so 0.8 of negative 41.7455 plus 0.4 of 81.7728, then minus 28.32, so negative 29.007 kilonewton meter. That's also the final value. So we haven't yet solved the slope and the deflection at E. So we have moment DE. So moment DE is because it's negative 90, because up E it is zero moment. We expect zero moment up E. So we use the alternate formula, slope deflection formula, which is 3EI over L, quantity theta near, which is in this case theta D, minus P, and P is delta over L, so delta E over 3. The assumption here is the rotation is clockwise, so we imagine that E is below the original E. So the bending is clockwise, or the rotation of the chord is clockwise. So that's why we use the same formula. Theta near, theta D minus, remember, minus P. And P is delta E over 3. With the assumption that E is, the final location of E is below the horizontal line DE. So it's here, so that the rotation is clockwise. And because we imagine that D and E are fixed and the load is only acting at the fixed end, there will be no fixed moments involved. So that's why we have to subtract 0. So simplifying this, we can now solve delta E. Delta E is equal to positive 515.3184 over EI. And the reason why it is downward, it's because it's positive. Our assumption is correct that the final position of E is below the horizontal axis E. So because the result is positive, it means that our assumption that E is below the horizontal line DE is correct. So that's why it's downward. If the result is negative, it means that our assumed direction, that assumed rotation, that DE is clockwise, is wrong. So it is above. And the deflection at E would be positive for that case. I hope you get the idea. Then for theta E, we have to set up moment EB. By the way, moment at E0 because that's the end. And this time we use 2EI because there is moment at D. Moment DE, we use 3EI over L because there's no moment at E. So remember, I hope you can distinguish the two formulas. So moment ED0 equals 2 times EI, which is 1. So delta E is negative 515.3184. So moment ED is 0, E to D 0. So 2 EI over L, 2 theta E plus theta D, which is this result, then minus 3 times delta over L. So delta over L, because the rotation is clockwise and this is positive, so delta would be 515.3184 also, because the assumption is clockwise, and that's correct. It's below or negative deflection. So remember that delta is the vertical distance between D and E, and that's correct. So 515.3184 divided by L3. So solving for theta E is equal to 216.7728 clockwise, but clockwise rotation is actually negative, so the final answer is negative 216.7728 over EI for theta. So that's it. Then for reaction at C, so we consider BC. We sum up moment about B equals 0. So shear at C just to the left times 8 plus whatever the moment at B or moment BC, which is 80.396. But let's put the moments and the direction so that will be our guide to solve for shear at C just to the left. So shear at C just to the left times 8 plus moment B, which is 80.396, equals moment at C, which is 29.007, plus the moment of this triangular load about B. So 1 half, 4.5 times 27. This moment arm is 3 plus 2, so 5. So shear at C just to the left is 31.545 kilonewtons. Then summation, no, consider CD. We sum up moment about D. So shear at C just to the right times 5 plus 30 times 3. So V sub CR is 14.201. So considering CD, shear at C just to the right times 5 plus 30 times 3 equals moment at C, which is 29.007 plus 30 times 3 plus 42 times 1. So you'll get VCR equals 14.201. So solving for R sub C, R sub C is the sum of VC left and VC right. So VC left is 31.545 and VC right is 14.201. So R sub C is equal to 45.746. Example 5 is about computing displacements of a simply supported beam or a determinate beam. So this is the problem. For the beam loaded as shown, find theta A, theta B, delta B, theta C, delta C, theta D, theta E, and delta E. EI is constant. So first, let's solve for the reaction at A so that we can find the moment at B and moment at C. So by the way, moment AD is, we use 2EI over L because there is moment at D. So moment at A is 0. So 2 times 1 over L, L is 9, quantity 2 theta A plus theta D, there is slope at D also, minus 3 times 0 because the chord joining A and D is horizontal. Then minus the fixed moment, which consists of the fixed moment due to this trapezoidal load and fixed moment due to this uh, concentrated 12 kilonewton load. So the height of the strip, if x is the distance from C to the strip is x, then imagine that the triangular loading is, the intensity is 30 minus 15, so 15. 15 divided by 3 is 5. So therefore, the height of the strip is 15 plus 5x. So that's why we have here height of strip 15 plus 5x dx times distance of the centroid of strip from A is, because this is x, so this distance is 6 minus x, and the distance of strip from B is x plus 3. So that's why x plus 3 squared over 9 squared, 0 to 3. That's the height of the strip, and that is 15 plus 5x. So minus the fixed moment of the 12 kilonewton load, which is 12 times 6 times 3 squared over 9 squared. So 2 theta A plus theta D equals 3015 over 8. So call this equation 1. Likewise, if you set up moment D to A, take note moment at A is 0. So we use the alternate formula 3EI over L, quantity theta D, theta near minus P, then plus fixed moment at D minus 1 half fixed moment at A. Remember the formula. And D is in the right side, so fixed moment at D due to this loading would be positive. Fixed moment at A due to this loading would be negative by slope deflection equation. So moment DA, by the way, is positive 30 because moment DE is negative 30. 15 times 2, that's negative 30. So moment DA is positive 30. So 3EI1 over L9, quantity theta near, D is near, so theta D minus P delta over 9. So delta is 0 because again, A and D are supports. Then plus the fixed moment at D is positive because if this is right of A, the fixed moment at A would be negative. Remember the principle by slope deflection equation. So integral of 15 plus 5x dx, then the distance of 15 plus 5x from D is x plus 3. The distance from A is 6 minus x. So this time 6 minus x is squared opposite to that. Then plus 12, this time is squared, 6 squared, then times 3 over 9 squared. Simplifying, you'll have, we can now compute theta D. Then minus 1 half fixed moment at A, which is negative of 15 plus 5x, distance of A from the strip is 6 minus x, then its distance from the right is x plus 3 squared over 9 squared, just like this one. But minus negative because the fixed moment at A is negative because it is in the left, plus 12 or still negative. So 12 times 6 times 3 squared over 9 squared. So take note that only theta d is the unknown here. So simplifying, 30 equals theta d over 3. This is 70.5, that's 16. Then minus of negative means plus, so 0.5, 75.75, then that's the second is 8. So solving for theta d is negative 295.125 over EI. And this is counterclockwise, and counterclockwise is positive. So theta d is actually 295.125 over EI. And that's positive. Then for theta A, substitute in equation 1, we can now compute theta A. 2 theta A minus, we use the original value because this is by slope deflection equation, equals 3015 over 8. So theta A is positive 336 over EI, and that means clockwise. And clockwise rotation is negative with respect to the universal system. So that's the final answer for theta A is negative 336 over EI. Then for DE, so we have moment DE. We imagine that E is below so that the chord rotates clockwise also. That's positive. Moment DE is negative 30. And because moment at E is 0, so we use the formula 3EI over L, quantity theta niya, theta D minus P, which is delta E over L, which is 2, plus fixed end moment. There's no fixed end moment because we imagine that D and E are fixed ends and the load is acting at the fixed end, so no moment will be generated. So, but before that, let's solve for the reaction at A. So, summation moment about D is 0, RA times 9 plus 15 times 2 equals the uniform load 15 times 3 times 4.5 plus moment of the triangular load 1/2 or 0.5 of 3 times 15. Moment arm is 2 plus 3, so 5. Then moment of the 12 kilonewton load 12 times 3. So RA is equal to 107 over 3 kilonewton meter, so that if you want to know the moment at B, the moment at B is simply reaction times 3. So moment at B is 107 over 3 times 3, so 107 kilonewton meter. Meaning, moment BC is 107 kilonewton meter, while moment BA is negative. Because this is positive, it means moment BC or moment BD. And moment BA is the negative of 107. So that's the meaning of 107 kilonewton meter moment at B. So moment B to D is positive 107, while moment B to A is negative 107 kilonewton meter. Then the moment at C is equal to RA, 107 over 3 times 6, then minus 15 times 3 times 1.5, minus triangle 0.5 times 3 times 15 times 2, then of course, there's no moment for the 12 kilonewton load at C. So moment at C is positive 101.5 kilonewton meter. Again, moment CD is positive 101.5, while moment CA is negative 101.5 kilonewton meter. That's the meaning of that. So moment AB, therefore, let's consider AB. Moment A to B is 0, moment at A is 0, because we expect moment at B, so we use 2EI, 2 times 1 over L, 3, the span AB is 3. Quantity 2 times theta A, which we already computed, and we use the result theta A from slope deflection, not from the final answer. So 336 plus theta B, then minus 3 times delta B over 3. Again, we imagine that B is below the original beam. It's here, so that the chord rotates clockwise again. So there's no issue with regard to our formula. It's remained the same. So minus 3P, still 3 times P, which is delta B over L. Then because there's no load between A and B, the fixed moment will be 0. So from there, we can set up the first equation, which is theta B minus delta B equals negative 672. Call that equation 1. Likewise, we set up moment BA, and moment BA is negative 107. Because A has no moment, we use the other formula, 3EI over L, quantity theta near minus T, then minus or plus fixed end moment B minus minus 1/2 fixed end moment at A. But because there are no loads between A and B, those will be negative. So moment dA is negative 107 equals 3 times 1 over 3 quantity theta B minus delta B over 3 plus nothing because there's no load. So simplifying this equation, we have theta B minus delta B over 3 equals negative 107. So solving these two equations simultaneously, we can now solve theta B by slope deflection. Remember, that's not the final answer. And delta B would be 847.5. So because the result is for delta B is positive, so the assumption that the chord AB rotates clockwise, so delta B is below, is correct. But the final answer would be for theta B negative 175.5 over EI, for delta B would be negative 847.5 over EI. Next, we consider moment AC and CA. So moment AC is 0. So because we expect moment at C, so 2EI over L, quantity 2 theta A plus theta C minus 3 times delta C over 6. Again, we assume that C is below so that the rotation of the chord AC is still clockwise. So there's no issue with regards to our equation. Then minus fixed end moment at A, because A is left, so it's negative. So it is equal to integral of 15 quantity 15 plus 5x dx. Distance of the strip from A is 6 minus x, while its distance from C is x. So that's why you have 6 minus x times x squared divided by 6 squared, 0 to 3. So simplifying, theta C minus delta C over 2 or minus 0.5 delta C equals negative 9,591 over 16. Call that equation 3. So we also have moment equation CA. So again, for CA, because A has no moment, we use 3EI over L. And moment CA is equal to negative 101.5. So 3EI 1 over L6 times theta C, or theta near, which is theta C minus P. Again, the rotation is clockwise, so minus delta C over 6. Because C is right of A, so the fixed moment here is positive. So we copy this integral expression, except that the squared term is now at 6 minus x, and x squared before will now be x here. So divide by 6 squared. So simplifying this equation, we have plus minus fixed moment at A, which is so minus 1/2. Then remember the fixed moment at A is negative, so we use the same integral. We change just the sign, the squared term. So 6 minus x this time, x squared over 6 squared. So remember that if the fixed moment first formula is negative, then it should also be negative here. But if it is positive here, it should also be positive here. So that negative 1/2 times negative is positive. So simplifying, this is 783 over 16. This integral here is 387 over 32. And combining and simplifying, theta C minus delta C over 6 equals negative 5201 over 16, equation 4. Solving equations 3 and 4 simultaneously, we get theta C equals negative 187.875 over EI, and delta C is 823.125 over EI as far as slope deflection equations are concerned. But for the final answer, remember, we just take the negative of these answers. So theta C is 187.875 over EI, and delta C is negative 823.125 over EI. Then the only unknowns here would be theta E and delta E. So let's consider DE. Moment DE, D has a moment which is negative 30 while E is no. So the formula would be 3EI over L, quantity theta D, here D minus P, then minus fixed end moment at D minus 1/2 fixed end moment at E. But because the loading between D and E is at the end, which is imagined fixed, therefore there's no fixed end moment. So by the way, we again assume that E is below, so that the rotation of the core DE is clockwise. We have no issue with regards to the formula. So moment D is negative 30 equals 3EI over L, which is 2 this time. Then theta D minus delta E over 2, or P, where P is delta E over 2, and we assume that delta E, or the final position of E, is below, so that the rotation of the chord is clockwise. So solving this equation, we can solve for delta E this time. So delta E is negative 550.25 over EI. And for theta E, we have to set up moment EB. So delta E, by the way, is positive because this is negative. So delta E is positive 550.25 over EI. So that means E is above. So this will bend that way. So E is above the horizontal axis ADE. Then moment E to D, because D has a moment, we use 2EI over L. So 2 times 1 over L2, 2 theta E minus plus theta D, which is negative 295.125 minus 3 times negative 550.25 over 2, because delta E is negative. So solving for theta E, the only unknown here, theta E is negative 265.125 over EI, but the final answer for theta E is positive 265.125 over EI. So I think everything is addressed. So that's the complete solution. So our last example would be a beam with support settlements. So for the continuous beam shown, some supports undergo settlements as indicated. Determine the nodal displacements and reaction forces. E is 200 gigapascals and I is 200 times 10 to the 6 mm to the 4th. Or in other words, EI is 40,000 kilonewton meter square. So first, let's have in preparation. We have a strip here. So there's no problem, 50x. Let's call the distance of the center of the strip from the left end of the load as x, or from the right end of the load from B as x. So its distance from A is 6 minus x. For portion BC, our x would be distance of strip, centroid of strip from B, so that's x. So its distance from C is 7 minus x. Then for this triangular load, the distance x is from the zero load, 0 end. Then 60 divided by 6 is 10, so the height of the strip is 10x. So moment AB can now be set up, theta E is 0. So moment AB equals 2 times EI, 40,000 over L, times 2 times 0 plus theta B minus 3 times delta over L. Our delta, because A to B is rotating clockwise, so we still use minus delta, minus 3 times delta. And delta is 0.015 meter, 15 mm, or 0.015 meter divided by 6. Then minus fixed moment at A is negative, integral of 50 dx times 6 minus x, x squared over 6 squared. So that's the integral. So simplifying, we have moment AB equals 40,000 over 3 theta B minus 100, this value here, the second term, then minus the value of the integral, 3125 over 24. Simplifying, moment AB is 40,000 over 3 theta B minus 5525 over 24. Call that equation 1. Moment BA, on the other hand, is the same. 2 times 40,000 over 6 times 0 plus 2 times theta B minus 3 times 0.05 over 6 plus integral of 56 minus x squared x over 6 squared dx. So it's now plus because it's B is in the right. So simplifying, moment B is 80,000 over 3 theta B minus 100, then plus the value of the integral 10,625 over 72. Simplifying, MBA is 80,000 over 3 theta B, then plus 3425 over 72, equation 2. Next, we proceed to BC. So B to C, remember B is here, then C is here. So C is above B. The rotation therefore is counterclockwise. And counterclockwise rotation by slope deflection equation is negative. It's very opposite to the general convention. So delta is negative 0.005 in the formula, where negative 0.005 is negative 5 mm divided by L7. So moment BC is 2 times EI, 40,000 over 7 times quantity 2 times theta B plus theta C minus 3 times negative 0.005 over 7 minus fixed moment, which is integral of 50 dx times x times 7 minus x squared over 7 squared. So x 7 minus x squared over 7 squared. Simplifying, moment BC is equal to 160,000 over 7 theta B plus 80,000 over 7 theta C plus 1,200 over 49, then the value of the integral minus 23,600 over 147. Simplifying, MBC is 160,000 over 7 theta B plus 80,000 theta C over 7, then minus 20,000 over 147. Call that equation 3. Then we have MCB. MCV is 2 times 40,000 over 7 times theta B plus 2 theta C minus 3 times negative 0.05 over 7 plus integral of 50 x squared 7 minus x over 7 squared dx. So MCB is 80,000 over 7 theta B plus 160,000 over 7 theta C plus 1,200 over 49 for this settlement, then minus plus 12,800 over 147. Combining or simplifying, MCD is 80,000 over 7 theta B plus 160,000 theta C over 7 plus 16,400 over 147, equation 4. And we proceed to CD. Again, the rotation of the chord CD is clockwise, so the delta over L ratio is positive. Delta this time is 0.03. 40 mm minus 10 is 30 mm. 30 minus 0.03. So MCD is 2 times 40,000 over 8, quantity 2 theta C plus theta D, then minus 3 times 0.03 over 8, minus integral of 10x dx times 6 minus x times quantity x plus 2 square over 8 square dx. So distance of straight from left is 6 minus x. Distance of straight from right is x plus 2. So that's why we have x plus 2 square over 8 square. Simplifying, MCD equals 20,000 theta C plus 10,000 theta D minus 112.5, then minus 150.75. So simplifying further, 20,000 MCD, 20,000 theta C plus 10,000 theta D minus 263.25, call that equation 5. And moment DC, moment DE is negative 60 times C, negative 180. So moment DC is positive 180. So moment DC is 180 positive, 2 times EI over L, theta C plus 2 theta D minus 3 times 0.03 over 8 plus fixed moment integral of 10x times quantity 6 minus x squared x plus 2 dx over L squared. So 180 equals 10,000 theta C plus 30,000 theta D minus 112.5 plus 74.25. Simplifying, 10,000 theta C plus 20,000 theta D equals 218.25. This is our working equation to solve for thetas. So call that equation A. Apply equilibrium at B, MBC plus MBA plus MBC equals 0. So MBA is 80,000 over 3 theta B plus 3425 over 72, and BC is 160,000 over 7 theta B plus 80,000 over 7 theta C plus or minus 20,000 over 147 and equals 0. Simplifying, So 49523.80952 theta B plus 80,000 over 7 theta C equals 88.48498. Call that equation B. Then equilibrium at C, MCD, which is equation 4, plus MCD, which is equation 5, equals 0. So quantity 80,000 over 7 theta B plus 660,000 theta C over 7 plus 1640 over 147 plus 20,000 theta C plus 10,000 theta D minus 260.25 equals 0. So combining like terms, 80,000 over 7 theta B plus 30,000, 300,000 over 7 theta C plus 10,000 theta D equals 151.685 equation C. So solving equations A, B, and C simultaneously using your calculator, we will put the answers on the next slides. So we get theta B equals 0.001641644 radian. Theta C 6.2864644 times 10 to the negative 4 radians. And theta D 0.010598177 radians. Remember that these are the values with respect to slope deflection equation, but with respect to the global coordinate system, the final answer should be their negatives. So theta B is negative 0.001641644 radian. It means the rotation is clockwise because that's negative. Negative clockwise rotation also of the tangent. And theta B clockwise rotation of the tangent. So solving now for the moments. So these are the direction of moments. Support. So moment at A is moment AB, 40,000 over 3 theta B minus 5525 over 24, which is the equation in the preceding slide. So moment AB is negative 208.32 kilonewton meter, and that's the final answer because it is counterclockwise. Moment B is moment BC, so 160,000 over 7 times theta B plus 80,000 over 7 times theta C using this slope deflection results minus 20,000 over 147. So moment at B is negative 91.347 kilonewton meter. Moment at C is moment CD, so we use the moment CD formula, 20,000 theta C plus 10,000 theta D, then minus 260.25. Moment at C is negative 144.695 kilonewton meter. And of course, moment DE is negative 180. So next, let's consider AB to solve for reaction at A. We sum up moment about B equals 0. So RA plus MB, which is 91.347, equals MA, which is 208.32, plus the moment of the load, 50 times 5 times 2.5. We sum up moment about B. So R sub A is 123.662 kilonewtons. Then we can solve shear just to the left of B by summing forces Y. So shear just to the left of B plus 123.662 equals 50 times 5, the load. So shear at B just to the left is 126.338 kilonewtons. Next, let's consider BC. Summation moment about C equals 0. So we have shear at B just to the right plus moment at C, which is 144.695, equals moment at B, which is 91.347, plus moment of the load 50 times 4 times 5. So shear at B just to the right is 135.236 kilonewtons. So we can also solve reaction at B, which is shear at left at B and shear just to right of B. So 126.338 plus 135.236. Reaction at B therefore is equal to 261.574 kilonewtons upward. Next, let's consider CD to solve for shear at by the way, summation forces Y to solve for shear at C just to the left. So shear at C just to the left plus 135.236 equals moment of the load 50 times 4. So shear at C just to the left is 64.764 kilonewtons. Let's consider CD, summation moment at B equals 0. So shear at C just to the right plus 60 times 3 equals moment at C 144.695 plus moment of the load 1 half or 0.5 of 6 times 60 times 4 plus 2 is 6 moment time. So VCR is 130.587 kilonewtons. So R sub C is V sub C left plus V sub CR. So 64.764 plus 130.587, R sub C therefore is 195.351 kilonewtons. Next is R sub D. You may have summation versus Y on D. So R sub D time or moment, summation of moment about C equals 0, RD times 8 equals or plus moment at C 144.695 equals 60 times 11 plus moment of the load 1 half of 4.5 of 6 times 60 times 2. 1/3 of 6 is 2. So R sub D is 109.413 kilonewtons. So we have to compute for theta E and delta E. So we have slope deflection for portion DE. We assume that E is below. So the rotation DE is clockwise. There's no fixed moments because we imagine D and E are fixed, right? So by experience, there will be no fixed moments generated. So the formula is 3EI over L times theta D minus delta E over L, which is 3. Then there are no fixed moments. So that's the equation only. So moment DE is negative 180 equals 3EI over L3 times theta D minus delta E over 3, then minus fixed moment 0. So again, our assumption here is E is below the original axis. If the result is positive, our assumption is correct and delta E is negative. But if the result is negative, it means that E is above horizontal line DE. So delta E is 0.04529 meter, and because it's positive, our assumption is correct that the deflection at E is downward. So that's beyond 40. In other words, if we draw the elastic curve, so delta E here, with reference to this settled support, we have 0.04529 meter below this settled support, or that's negative. So therefore, delta E in mm is negative 45.295 mm. Okay, you convert that to mm. For theta E, we set up slope deflection equation ED. There's no moment at, there is moment at D. So the formula is 2EI over L. So 2 times EI 40,000 over L, and 0, moment ED is 0, equals 2 times 40,000 over 3 times quantity theta D plus 2 times theta E minus 3 times delta over L. So we go back to the original delta by slope deflection equation over L. Plus, there's no fixed moment equation. So solving for theta E, which is the only unknown here, theta E is equal to 0.01734841115 radians. But the actual theta E is, because the rotation is clockwise definitely, is this is clockwise, and clockwise rotation is negative. So negative 0.01734841115 radians. So that's all for this problem. As our last example, let's consider a problem where the load is a couple. So consider the beam shown subjected with a couple load. And we already computed this by the area moment theorem. Oh, sorry, the three moment equation. So this is the beam simply supported, and that's the deflected shape, and that's the expected delta B, and this will be the reactions. So first we write slope deflection equation for span AB. That is, although this is the moment diagram, we simply do not consider that. Moment AC is 0, that because the movement at the far end is 0, so we use 3 EI over L. Quantity theta near, which is theta A minus 0, because fixed moment at A, because it is in the left, is negative. Moment B over L square, the formula, and moment is negative because the applied couple is counterclockwise from the formula. M is positive if it is clockwise. We just treat everything as positive. Then if the result is positive, it's really clockwise. But we consider negative 120 as negative 120 here. So the formula is moment B over L squared times quantity 2L minus 3B. So moment is taken positive, negative because the couple is counterclockwise. The formula, when we derive the formula for a couple, was clockwise. Then L square is 10 square, quantity 2L, 2 times 10 minus 3B. B is the distance of the couple from the right support, which is 6. Then minus fixed moment at C, which is treated positive, so minus 1 half, negative 1 half of, because the moment is negative again, so negative 120. A is 4 this time, divided by L square, quantity 2L minus 3A. So simplifying that equation, we can solve theta A directly. So theta A will be negative 16 over EI, and because this is slope deflection equation, the meaning of negative 16 over EI is counterclockwise. But counterclockwise is positive direction of positive rotation, so theta A is 16 over EI, just like the answer in double integration. So positive, and that's counterclockwise. Then, if we have moment AC, we also have moment CA. We have the same formula. Moment at C is 0. So moment CA is 0 equals 3 EI over L10, quantity theta C minus delta, which is 0 because we consider two supports, then plus moment at C, which is formula moment, positive moment, negative 120 because counterclockwise. Moment is counterclockwise. Then A is 4 divided by L squared, 2L minus 3A minus 1 half. Moment at A is equal to negative of 120, 6 over 10 square times 2L minus 3B. 6 is B, because moment at A is M over MB over L square, quantity 2L minus 3, which is that. So simplifying this equation, we only have theta C as the unknowns. So we'll get theta C equals negative 104 over EI. Again, negative means counterclockwise, so theta C is positive 104 over EI. So for AB, this time to solve for delta B and theta B. So moment AB equals, because we expect moment at B, moment at A is 0, so the other formula is 2 EI over L. L is 4. And we imagine that B is below, so that the rotation of the cord is clockwise, and there's no issue with our equation here. So 2 EI over L, 4, times quantity 2 times theta A, which is based on slope deflection, it's negative 16 over EI. Do not use the final answer, but based on the slope deflection, because this is slope deflection equation, plus theta B, then minus 3 positive delta, because our assumption is delta is below B here, so that the chord AB rotates clockwise, over L, which is 4. And there's no fixed moment, as I said, because we imagine that A and B are fixed, and there are no loads in between A and B, so that's why there are no fixed moments. So simplifying this equation, we have theta B minus 3/4 or 0.75 of delta B equals positive 32. So call this equation 1, where positive 32 is 2 times negative 16 transposed to the left equals 0 times 4 over 2 is still 0. Likewise, we also have MBA, but MBA this time is, because MBA is 48, it's counterclockwise, but we expect clockwise as positive for slope deflection, clockwise positive, that's counterclockwise. So we treat 48 as negative, and since moment at A is 0, we use the other formula 3EI over L. So moment BA is negative 48 equals 3EI over L, which is 4. Quantity theta near, theta B minus delta over 4. Delta B over 4. Which is, because our assumption again is B is below, so rotation is counterclockwise, is clockwise. If you have B to A, the rotation of the chord is also clockwise. It doesn't change. So simplifying this equation, we have, by the way, that's the explanation, negative 48, because it is counterclockwise, and from slope deflection equation, clockwise must be positive, or clockwise positive. So that's why it's negative. So the equation is theta B minus 0.25 delta B equals negative 48 times 4 over 3. And that's theta B minus delta B over 4 equals negative 64, equation 2. Solving these two equations simultaneously, we get theta B by slope deflection equation, negative 112 over EI, wherein the meaning of negative 112 over EI is, it is counterclockwise. So theta B is positive 112 over EI. That's the final answer. And delta B is negative 192 over EI. Because it is negative, it means the rotation is not really clockwise, it's the opposite way. So delta B is positive, and B, the final position of B should be above the horizontal B here. It lies on the x-axis, it should be above, because the result of delta B is negative. If it happens to be positive, then the assumption that B is below is correct, but the sign of delta B would be negative also, because it is downward. But because delta B is, or the final position of B is above the original B here, then delta B is positive. So delta B is 192 over EI. So that's it. So again, to summarize, theta A is 16 over EI counterclockwise. Theta C is negative because the value of theta C from slope deflection is positive, so meaning clockwise, and clockwise is negative, so theta C is negative 104 over EI. Or in other words, that's counterclockwise. That's clockwise rotation. Then the theta B is 112 over EI, and the slope is rotating counterclockwise, and that's positive. These are the results by slope deflection. Delta B is 192 over EI, and that's a positive deflection.
Okay, let's solve this example 8, our last example, and the last situation for beams. By slope deflection equations, compute the support moments and reactions. EI is 40,000 kilonewton meter square. Joint A rotates 0.002 radian clockwise. So this is the figure, and the important items to be determined would be the moment at A and the moment at B. So let's just solve moment at A and moment at B, then the rest of the reactions can be found, and I will leave that to you as your exercise. So first, let's set up moment equation for AB. Moment AB, because EI is 40,000, is 2 times 40,000 over L6, quantity 2 times 0.002, positive because it's clockwise, plus theta B, minus 3 times delta. Delta is 0.03 divided by L6, 0.03 meter, 13 m divided by 6, and this is treated positive because the rotation of the chord is also clockwise from slope deflection equation conventions. Then minus plus fixed moment at A, which is negative, from sign convention, so negative 60, 3 square over L square, which is 6 square. So simplifying, moment AB is equal to 160 over 3 plus 40,000 over 3 theta B minus 200 minus 45. So after expansion and simplifying, moment AB is equal to 40,000 theta B over 3 minus 575 over 3. Call that equation A. Then for moment BA, it is 2 times 40,000 over 6 times quantity 2 times theta B plus 0.002 minus 3 times delta over L 0.03 over 6. Then it's the fixed moment here is positive. It's the right. So 63 3 square over 6 square. So MBA is equal to 80,000 theta B over 3, then minus 85 over 3. Call this equation B. For moment BC, B is lower than C by 10 mm, and the rotation of the cord, imaginary cord, is counterclockwise. So both the theta would be negative in the slope deflection equation. Delta is also treated negative, negative 0.01 meter or 10 mm, negative 10 mm over L, which is 8. So MBC equals 2 times 40,000 over 8, quantity 2 times theta B plus theta C, which are both unknowns, minus 3 times delta, as I told you, negative 0.01 over 8. Then fixed moment WL square over 12, so negative 38 square over 12. Simplifying, MBC equals 20,000 theta B plus 100 plus 10,000 theta C minus 122.5. Equation C. Then moment CD, we know that the moment at C is, moment CD is negative 30 times 2 times 1. Negative 30 times 2 times 1, moment CD. So that is negative 60, but moment C to B is positive 60. So moment CB is 60 equals 2 times 40,000 over 8, quantity 2 theta C plus theta B minus 3 times negative 0.01 over 8 plus fixed moment positive 38 square over 12. So simplifying this equation, combining like terms, we'll have 10,000 theta B plus 20,000 theta C equals negative 137.5. Call that equation 1. Then we apply equilibrium at B. Moment BA plus moment BC equals 0. Moment BA, 80,000 over 3 theta B minus 85 over 3 plus moment BC, 20,000 theta B plus 10,000 theta C minus 122.5 equals 0. So the result would be 140,000 over 3 theta B plus 10,000 theta C, then equals 1,505 over 6, equation 2. So if you solve these two equations simultaneously, you can solve theta B and theta C, and we get theta B equals 0.00767 radians, and theta C is negative 0.01071 radians. So theta B means, because this is positive, the tangent is rotating clockwise, then theta C is rotating counterclockwise from the sign convention in slope deflection equations. So finally, we can solve now moment at A, which is defined by this moment AB here. So 40,000 times quantity 0.00767 radians over 3 minus 575 over 3. And it will give us moment at A equals negative 89.4. Then moment at B is represented by moment BC. So let's substitute into moment BC, 20,000 times 0.00767 plus 10,000 times negative 0.01071, then minus 122.5. So moment at B is equal to negative 76.2 kilonewton meter. So stand by for the other methods of solving this problem by double integration, by three moment equations, by moment distribution methods. I also solved this by method of least work. So stand by in my uh, other videos, especially this problem here, because this is solved by other ways. So that's all for this series, and I hope that all these examples will cover all the expected problems that you should encounter in the theory of structures. Thank you and bye-bye.